Okay, so welcome back to the third hour. What we have derived now during the second hour was this equation number 4 that is written here on the screen, which is an equation now in f prime, f double prime. F prime, again, that's the u velocity. F is the integral of the u velocity, and or the integral of f prime. And f triple prime is, of course, the first derivative of that. So we have an equation in f triple prime, f double prime, f, and f prime. And then we have a few coefficients, g1, g2, and g3. And now our claim is that if these coefficients g1, g2, and g3, if these are only functions of eta and not of x and y, then we actually have the possibility of reaching a self-similar solution. If these coefficients are depending on x and y, that means that self-similarity is not possible because we have additional dependencies which we cannot get rid of. And we're not really interested in those solutions right now. So it means for us to understand when we have self-similar solutions and then also how to solve those, we actually need to look at these coefficients g1, g2, and g3. So let me just write them down. So g1 was d squared eta dy squared divided by d eta dy squared. This was g1. Then we have g2, which is composed of two parts. The first one would be d squared eta dx dy, and then we have d eta dy squared again in up to the power of 3, and then this is ue of x times nu. And then we have g3, which is 1 divided by d eta dy squared times 1 over nu times due of x dx. So these are these three coefficients, g1, g2, and g3. I think it's also important to realize that up to now, our approach is actually general. So the only thing that we did was we started from the boundary layer equations. We didn't start from Navier-Stokes. So we assumed that we have a boundary layer in the sense that the variations in y are much larger than the variations in x. That is the only assumption that we have done so far. Apart from that, it's still general. In particular, we have not made any assumption for ue of x. So that means our approach is still general for any free stream velocity distribution. There is no limitation to only having constant or growing as a square root or anything like that. It's a fully general approach. The only assumption is boundary layer equations. But the variations of u of x, they are still completely general. So that means now, I guess, to get any further, we actually need to start to make such assumptions for the free stream velocity distribution, because we may want to kind of zoom into one specific type of solution. And of course, the first one, I guess, the most known of these solutions would be, and I call this now part A. Part A, and that would be the Blasius Blasius solution. So the Blasius solution is the solution for a flat plate boundary layer or a zero pressure gradient turbulent boundary layer. So that's a solution for a flat plate boundary layer. Of course, that's in that sense the most canonical case that we can really think of. This is also called a zero pressure gradient boundary layer. Zero pressure gradient at times is abbreviated with ZPG. Zero pressure gradient, of course, means dP dx is zero, and dP dx, now using the Euler equations, means that u of x is actually constant. And this can be, because it's constant, we can just call it u infinity, which is the typical variable that we use for zero pressure gradients. So that means if I draw that, this Blasius boundary layer would look like this. We have an x and y coordinate here. We have our boundary layer growing like this. And if we now have a boundary layer profile here and another one here, we know that the free stream velocity is u infinity in both cases. So that is constant. So that means that there is no rescaling necessary in terms of the velocity. The only scaling is related to the growth of the boundary layer. So kind of these lines that I have now indicated, so that the profile is only stretched in the vertical direction. The boundary conditions, again, for the Blasius case, are of course one boundary condition here. So this is boundary condition 1, which is the no slip boundary condition. And then up here, we would have boundary condition number 2, which means that the velocity far away is just u infinity, a constant u infinity. Now, as I was saying, this is called the Blasius solution. Now, why is this called Blasius solution? Well, it was first derived by a person that is called Heinrich Blasius. And Heinrich Blasius, he lived 1883 to 1970. And he came up with this Blasius solution in 1908. Actually, this was his PhD thesis, which essentially just was deriving this equation, of course, analyzing it as well. But keep in mind that we said before that Ludwig Prandtl, he came up with the boundary layer equations in 1904. So it was 3-4 years after that, then the first actual solution to the boundary layer equations were derived by Blasius. And as I said, Blasius did this as his PhD, and of course, his PhD advisor was Ludwig Prandtl, so they did that together. So what does it now mean if we restrict ourselves to zero pressure gradient when it comes to these G1, G2, and G3? Well, I guess one obvious thing is directly to see that G3, where you have due dx, if we now restrict ourselves to having constant free stream velocity, G3 will immediately become 0. So one immediate consequence is that G3 is actually 0. So that means now that our equation becomes f triple prime plus G1 of eta times f double prime plus, or that is equaling f times f double prime times G2 of eta. Now, of course, I wrote it in the way now that I assume that G1 and G2 are actually only functions of eta. But still, the first question for me is now still find an eta of x and y such that g1 of eta and g2 of eta are not functions, or actually, no, that's maybe sufficient if I just write it like this. So find an eta of x and y such that g1 is just a function of eta and g2. Actually, maybe I should write it like this. That's probably easier to understand. So that g1 is g1 of eta and g2 is g2 of eta. So that's now my job. Yeah, how do I do that? If I now look at g1 and g2, well, it's not obviously clear how I could do that. I see there's all kinds of derivatives here involved. Yeah, how could I do that? Well, there's of course one ansatz I can make, and I can see whether this helps or that leads anywhere. So let's make an ansatz. We say that this eta of x and y could be decomposed in a term y times some unknown function of x. Now, why would I like to do that? Why could this be a good ansatz? Now, let's not think about the mathematics behind it. Let's just think about the physics behind it. Well, as I was saying here, when we look at these profiles, what we would like to have is we would like to be able to scale the profile in the vertical direction. So that means that most probably for this eta, we need to have a linear y, which kind of gives us the height, which is scaled with a function of x. So that as x is changing, I will squeeze my vertical distance. But as the simplest way, let's assume that y is linear, and all the nonlinearity or the variation comes in the x term. And I guess physically speaking, this is a reasonable approach. So that essentially means what I'm doing is I'm scaling y, the vertical distance, by an x-dependent factor h of x. But I'm leaving y to be there linearly, being just scaled by x. So I guess that sounds like a useful approach. I'm not sure that it's correct, but it's certainly a valid approach. So now, if we do that, then we can calculate g1 and g2 by putting that in and replacing essentially eta with h. If we do that, actually, it's quite interesting to see that if I start with just looking at the various terms. So, for instance, we have this term d squared eta dy squared. If I'm doing that, then so d squared eta dy squared. Of course, this becomes then d of dy times d of dy of y times h of x. And now, of course, I see if I do h of x is not dependent on, like this, h of x obviously is not dependent on y, so I can take that out. But then I see that the first derivative with respect to y is 1, and then I take another one, then it becomes 0. So actually this becomes 0, meaning, and that's of course a nice result, g1 is also 0. Now means that this term actually disappears as well. And of course that's very nice because it makes our equation much simpler. So now it all depends on whether or not we can define a g2 that is independent of x and y. So that was this one. And then the second point would be to look at g2. Well, g2 of eta Well, that was u infinity divided by nu, and then we had d squared eta dx dy. That was divided by d eta dy to the power of 3. Now, if I'm putting in eta in the way that I have, and then I do all these derivatives that I have here, well, what do I get? So the first one is, of course, it's the same. So then I have d squared eta dx dy. Well, I guess this just gives me an h prime from the derivative with regard to x, and then I have the derivative with regards to y, which gives me the factor of 1. And then if I'm doing the derivative of eta with respect to y, I of course get h of x, and then this to the power of 3 gives me h to the power of 3. Actually, this is all a function of x. And now, in order for this to become constant, or in order for this to be a self-similar solution, this needs to be a function of eta only. But now, of course, I see it's a function of x here. X should not be. So that means this here can only be this can only be a constant because all the etas have disappeared. So this here needs to be a constant. So that means this equation sign, this is actually an ansatz again. An ansatz needed for similarity. If this was not the constant, I would not have a self-similar solution. Now, of course, I can choose what constant I want. Now, people typically use here a value of -1/2. You will see later on why -1/2 is a good value. For now, just believe me that choosing -1/2 is something good. Sometimes people also choose the value of -1 here. So for the Blasius solution, there's 2 different ways in the literature, which unfortunately, it's not always clear, or they're kind of mixed a little bit. Some people choose -1/2, some people choose -1. Of course, it gives the same result in the end, but the scaling is slightly differently. So one needs to be a bit careful. I personally choose -1/2. But I think Wikipedia, I'm not sure, chooses -1. But just keep that in mind. Anyway, if we now believe that, or if we agree with each other that this needs to be a constant, then actually we can continue here and try to solve this ordinary differential equation h prime divided by h to the 3 being -1/2. So I write like this: dh dx, that's h prime, is -1/2. Well, if I multiply this over, so we have nu divided by u infinity times h to the 3. So this is now an ordinary differential equation that I can solve for h. And I can solve that with the typical separation of variables approach, which means I put everything that depends on h on one side, everything that depends on x on the other side, and I integrate. So if I do that, I just multiply this by x and divide by h to the 3. So I get the, well, if I do it step by step, so I have 1 divided by h to the 3 times the h is -1/2 of nu divided by u infinity times dx. And I want to integrate that, so I put some integral signs here, and I can now perform this integral. I get -1 divided by h squared, which is the same as minus nu divided by u infinity. Yeah, the factor here with minus 1/2 has now gone away. And if I'm solving that, I get h of x being the square root of u infinity divided by nu times x. And this is now, so if I want to have my h, or if I define my h in this way, then I know that this expression here becomes minus 1/2. And now I guess you also understand why I chose 1/2, because that means that there is no factor in here. If I had minus 1 here, there would be a factor of 1/2 inside this, square root. And this I don't like so much. Okay. This, of course, is very nice, because now with knowing what h is, I know what my eta of x and y is, because I can just put in the h in here. So now I know with this I know this I know that my eta is y times the square root of u infinity divided by nu times x. This is my f of, or this is the definition of my eta. And I know it needs to be non-dimensional, obviously. So that means that actually this term here, or this part, needs to have the dimension of a length scale. And if I look at this, I can see it needs to have the dimension of an inverse length scale. So that means I can actually introduce here this length scale as being delta, or 1 over delta. So that means that actually this eta here is only a non-dimensionalization of my y coordinate with this delta. And this delta is what is called the Blasius length scale. And of course, the definition is exactly what is written here. That's the square root of of nu times x divided by u infinity. Of course, now you know, I think now everything makes sense. And actually, already at this stage here, you could have said, wait a second, at this stage here, wait a second, if I know that h here needs to, or I know at this stage that h needs to be the inverse of a length scale, so I can directly construct it based on, u infinity, nu and x. I wouldn't have gone through all of this. I could directly put it in at this point. Of course, this is correct. But now that we have done the whole derivation, of course, you see nicely that the expected result comes out that this h factor becomes actually an inverse length scale. So the only thing at the end of the day, what I'm doing is I'm rescaling my y with a length scale which somehow encodes the viscosity, the velocity, and the position along the plane. And of course, the cool thing now is, and I guess this relates a little bit to what we said in the beginning, I can now directly see that my y is actually proportional to x divided by the square root of u infinity x divided by nu. That this is what I get from this expression here. And of course, if I'm now if I replaced what I have in the square root here, then I get x divided by the square root of Reynolds x. And of course, this is exactly the relation that we had in the beginning of today's lecture when we talked about the thickness of the boundary layer. So this is as in the beginning. We have now recovered for the Blasius solution exactly this square root behavior of the growth of a boundary layer. Now we just have done it with a very nice formal derivation based on the boundary layer equations with all kinds of tricks. But in the end, the only approximations that we did was that we said it's boundary layer equations and that the free stream velocity is constant. And then we got this. Apart from that, this is an exact result. Okay, so now we have our definition of eta, and we also know our equation, the equation in F, because we have now G1 and G3 and G1 are 0, and G2 is defined as -1/2. So that means we also get the so-called Blasius equation, which is simply F triple prime plus 1/2 F times F double prime is 0. And this is an ODE. It's an ODE written in terms of the similarity variable eta. So F is a function of eta. As I was saying, some people write here a -1 instead of -1/2. Of course, that means, I would really like to add that here. Note, if I had chosen a -1 there, then the Blasius equation would be F triple prime plus F times F double prime. So without the 1/2 there being 0. But then the scaling of eta would be the following. Eta would then be y times the square root of u infinity divided by 2 nu times x. Now in my case, I have no 2 here, but I have a 2 here in the equation. That's just for completeness, because some people write it in a different way. But of course, the result in the end is the same when you take into account all these scales. But anyway, after this exercise in doing derivatives, now we have this Blasius equation, a self-similar equation. So all the dependencies on x and y is gone. Now we just need to write the boundary conditions, also in terms of f. And of course, this is not so difficult. We had boundary condition number 1. If you go to the sketch that we had here, so boundary condition 1 is just at the wall, where we say that f prime of eta being 0 is 0. So that's the no-slip condition. And then the second boundary condition is in the free stream. Again, f prime of eta going to infinity should be 1. That's in the free stream. Okay, are we done? Well, unfortunately not. There is actually one thing is missing here. Because, well, we have an equation here. The Blasius equation is of 3rd order. So that means we actually need for a 3rd order equation 3 boundary conditions. Right now, we only have 2 boundary conditions. So that means, unfortunately, we cannot solve it yet, or the system is not yet complete. So 1 boundary condition is missing. What boundary condition could that be? Well, what is it that we have not used? Well, we have here boundary condition 1, which is the no-slip condition, but we have only used the fact that u needs to be 0. We have not used the fact that also the v velocity, the vertical velocity, also needs to be 0. So at the wall, also v needs to be 0. Well, what is V? Yeah, well, V is V of y, what we wrote it above. This is this kind of integral term, minus d dx of the integral from 0 to y of u dy. And now, of course, this needs to be written in terms of f. Now we can do that. Now we know what f is. It's minus d dx of integral from 0 to y of u infinity times f prime of y, and not of y, of eta dy. And of course, now we need to work a little bit here to make that work. We need to replace this dy with the eta, and of course this we already have done implicitly before. But dy becomes d of well, square root of nu x divided by u infinity times eta, which is nothing else than square root of nu x u infinity of d eta, something like that. So essentially, we have scaled that in a proper way. So that means now if we put in this changed dy, we get as our v of y being minus u infinity of nu x divided by u infinity times d dx of 0 to y of f prime of d eta. And of course, this becomes now u infinity of h prime, now using definitions from before, h prime of x times minus f plus nu eta times f prime. Okay, so this is now what v of y is as a function of h and f prime. Of course, with this now we know that we can evaluate v of 0, which needs to be 0. That's the no slip boundary condition. And of course, this becomes now in light of this that minus f plus eta times f prime at y being 0 should be 0. Eta is 0, so f prime doesn't matter. So at the end of the day, this just means that f at eta being 0 needs to be 0. And that is now the third boundary condition. And now we're happy. Now we actually have a third order differential equation with 3 boundary conditions. And for completeness, I can write that up. So my ODE now becomes the following. My ODE is f triple prime plus 1/2 f times f double prime, which is 0. And my boundary conditions are f of 0 equals 0, f prime of 0 is 0, and f prime of infinity is 1. So that's my set of equations. And then if I want to go back to the velocities of once I have this, so my u would then be u infinity of f prime of eta. My eta is y divided by delta. My delta is square root of nu x divided by u infinity. And then finally, we also have the v. And my v is essentially u infinity times h prime of x times minus f plus eta times f prime. Something like that. And the h prime of x, I think we have written, we haven't written it explicitly, but essentially it's given here. when h is kind of introduced like this. Maybe, yeah. Maybe I can just, for completeness, I can write it. So the h here would of course be, well, 1 over delta, which is the square root of u infinity divided by nu times x. So now I think we have written down everything. So that means if we're now able to solve this equation, so we get a function f as a function of eta, and f prime and f double prime, we can then calculate based on that u and v. And of course, then I have my velocity field, and I'm very happy about that. And I can plot all my boundary layer profiles. The problem is, I guess that's the issue here, that the solution to this ODE is actually not an analytical solution. The solution to this system is not analytical. So that means we actually need to use numerical techniques to solve this system. So we need to use numerical techniques to solve it. Simple as that. Typically, the way that it's done, and I will show you also next time a small MATLAB code, a small MATLAB code that does it, or I will share it with you. So typically, this is done via an integration using Runge-Kutta, via a Runge-Kutta integration. Coupled, and now comes of course yet another difficulty in this, coupled to a so-called shooting method. I don't want to go into too much details on how you would do that numerically, because that would be kind of a course in numerical methods. But the basic problem is, if you look at this equation, you cannot just simply integrate it forward in eta, because you have boundary conditions at 0, which of course is good. But then we also have another boundary condition at infinity. So we have kind of a coupled problem where you have boundary conditions at 0 that need to fulfill somehow a boundary condition at infinity. So we cannot just integrate it in space. So therefore, what one does typically is one does a shooting method, meaning then that one assumes that one has a boundary value at 0 for f double prime, and then one evaluates it and sees what do we get at infinity, and then if it's too large or too low, we change then the value at the wall up to the point that we have iterated us forwards to getting the correct value at the wall. So that's what I mean when I talk about a shooting method. I provide, and today we'll not have time to go through that, but on the home page of this course, I'll provide a MATLAB file which is called blasius.m, which solves this equation, and you can of course go in and look at how this is actually being done. It's all done using MATLAB functions, so it's quite easy to kind of understand. But now that we have 5 minutes left for today, I would just like to sketch the solution that we get, and then next time we will also look at the numerical solution of it. But essentially, the solution will look something like this. And typically it's done like this, that on this axis I write the eta, which is exactly my delta, my y divided by delta. And then on the axis here, I plot f, I plot f prime, and I plot my f double prime. And maybe the easiest, now just to build up the plot, is to start with f double prime, because that's actually a nice function that starts here, is kind of constant, and then it goes to 0. So this would be f double prime. And as I was saying, the Wall value that you get, which is a numerical result, but still quite useful to know, is 0.332. We'll get back to this value. That's why I'm also kind of stressing it a little bit. The u velocity, f prime, looks something like this. Of course, this value here, now the scale is a little bit off. I should make it better. So this value is maybe like this. So this, of course, is reaching 1 for the free stream. And of course, that also means that it reaches 0.99 at a height which would correspond to delta 99. And of course, the question now is, where is this delta 99 in terms of our variable eta? But actually, it turns out, and we will talk about that later next time, this is reached at a value of 4.91. So this is, again, a numerical result. So this was the u velocity. And then we have also the f, which is a function that kind of looks like this. And it turns out that this will grow indefinitely, and it's proportional to eta when it comes to, for values far away. And of course, this the blue line, this corresponds to v, in the sense that v is u infinity times this h prime times minus f plus eta times f prime. Yeah, so just to summarize for today, now we have written the solution. F is related to v in exactly the way that I just wrote. F prime, that's the value that is related to u, or actually it's defined as u divided by u infinity. And the green line, so the f double prime, that is related to the derivative of u, and of course that means in this case that will be related to the stress. And of course now you can realize why this value here is actually important, because that actually corresponds to the wall shear stress. And of course this 0.332 will come back when we calculate CF, so the friction coefficient at the wall. But this is something we do next time. So for now, it's just important that you realize that the solution to this Blasius system that we have now derived today looks like this. You can obtain that with MATLAB. I will share the code with you and run it together also next time. But then if you have this, you can directly calculate what is my u velocity, what is my v velocity, and what is my stress, just based on this so-called Blasius solution. So let me just write that. So this is the Blasius solution. And as I said, this is not an analytical one. We need to use numerical techniques, but it's quite well understood how to obtain accurate solutions of this solution. Okay, with this, I would like to close for today and thank you for staying with me until 6. And as I said, next time, so on Thursday, we will actually meet in Forli at, well, 3 or maybe a little bit later than 3, depending on any delays. And then we will continue essentially looking at these various boundary layers. Okay. Thank you very much, and see you in 2 days.